Stanford University.
Let's just come back to fermions and bosons for a moment. And I'm not interested now in the motion. We've talked about this before. Just fermions and bosons at rest. They're described by creation and annihilation operators. You create a particle with a creation operator. You annihilate it with an annihilation operator. I'm not interested in their momentum. They're either there or they're not there. And we can describe them in terms of, you know the story, creation and annihilation operators. If we're talking about bosons, then we introduce creation and annihilation operators, A plus, A minus. We multiply them together. We multiply that expression by the mass of the particle, and just m A plus A minus, that's the mass, times the number of quanta. A plus times A minus is the number of quanta. And we can just say that's the energy. The mass times the number of bosonic quanta, that's the energy of the bosonic system. If we also add fermions in, we add fermions in by a similar pattern. Creation and annihilation operators for fermions we've called C. And if the fermions and the bosons have exactly the same energy, or mass, we can call it mass or energy, then we would just add to the number of bosons also the number of fermions, C plus, C minus. And that would be the thing we would call the energy or the Hamiltonian. Let me just say a word or two about the Lagrangian formulation of bosons and fermions. Again, we're concentrating now on just fermions and bosons without worrying about their motion in three-dimensional space. All right? For bosons, we invent a field. The field is called, also for fermions, but for bosons, we might call the field phi. We usually call it phi. And we give it a Lagrangian. Incidentally, just to remind you, this is nothing but the mathematics of a harmonic oscillator, of a single harmonic oscillator. All right? So to describe the field theory in this very, very simplified context, the field theory of the bosons is just a harmonic oscillator. We introduce a variable phi. It's like the coordinate of the oscillator, and we give it a Lagrangian phi dot squared over 2 plus the frequency squared, which is just m squared, phi squared over 2. To get spatial gradients, I'm not thinking about things varying in space or moving in space. This is the simplest situation, simplest setup. There's only a time direction, no space directions to worry about. And now we can work out the equations of motion, the Lagrangian equations of motion, straightforward. The derivative of the Lagrangian with respect to phi dot, remember what they are, the Lagrange equations of motion. Partial of L with respect to phi dot, d by dt, is equal to partial of L with respect to phi. All right, dl by d phi dot, that's just phi dot. This would give us the second derivative. So this just becomes a phi double dot, two-time derivatives, and that's equal, oh, I'm sorry. What did I do wrong here?
Sorry. Yeah, L minus, T minus V.
T minus V. Right. Energy is T plus V. Lagrangian is T minus V. All right, and that's equal to the derivative of the Lagrangian with respect to phi. That's equal to m squared minus m squared equal minus m squared phi. And the solutions of this is differential equation, second order differential equation. It has oscillating solutions, and the oscillations oscillate with a frequency m, not m squared, but m. And so, not surprisingly, the mathematics of all of this, the quantum mechanics of it is just the quantum mechanics of a single harmonic oscillator, one creation and one annihilation operator. As a ground state with no particles, you add particles with a dagger, you take them away with a minus, a you add particles with A plus, you take them away with A minus, and so forth. Now, let's come now to the fermions. The fermions, Lagrangian for fermions is in some sense simpler than for bosons. It only involves a first power of a time derivative. It doesn't involve phi dot squared. It's more like just phi dot times phi. Let's just think about that for a moment. Imagine we had a Lagrangian which was phi dot times phi. And let's suppose for the moment that they're bosons. Right? Bosons mean conventional. The phi's are, just think of them as a classical Lagrangian. The phi's are numbers. They're not Grassmann numbers. They're ordinary numbers. They commute with each other and so forth. Suppose this was a Lagrangian. Is this an interesting Lagrangian? Does it give an interesting equation of motion? All right, so let's work out the equation of motion. Partial of L with respect to phi dot, that's equal to phi. Then we have to take the derivative of that. So d by dt of this is just equal to what? Phi dot? And that should equal dl by d phi, which is just equal to phi dot. That's not much of an equation of motion. It puts no restriction whatever on anything. It just says phi dot equals phi dot. It's a tautology. Every possible trajectory satisfies it. The only thing you might want to say is, well, maybe the trajectories ought to be differentiable so that phi dot means something. But other than that, no restriction. It is not a useful or interesting Lagrangian. This is connected with the fact that this is a total time derivative. It's equal to 1/2 of the time derivative of phi squared. And whenever a Lagrangian is a time derivative of something, it's always trivial. It never gives an interesting equation of motion. Right? You can throw away total time derivatives out of a Lagrangian. Doesn't matter what it's a time derivative of. It just doesn't matter. It doesn't make any interesting equation of motion. But now let's suppose that phi was a fermionic variable. If it's a fermionic variable, it means it has to be treated like a Grassmann number. Okay? Partial of L with respect to phi dot, we differentiate with respect to phi dot, and that indeed gives us phi, and we take the time derivative of it. But what about partial of L with respect to phi? If phi and phi dot are Grassmann variables, and you differentiate with respect to phi, you have to push it past the phi dot, which is also a Grassmann variable. You get a minus sign. In other words, if you wanted to write this in the other order so that you could directly differentiate it with respect to phi, you would have to put a minus sign in. And so you would get partial of L with respect to phi is minus phi dot. What's the equation of motion now? It is phi dot is equal to minus phi dot. That seems equally stupid, but it's not. It's not equally stupid. Bring it over to the other side. It's twice phi dot equals 0, and it gives you some information. It tells you phi dot is 0. That's highly restrictive. It means the solutions are, they're highly restrictive, and this Lagrangian has some punch to it. Maybe too much punch for our tastes. Right? Maybe too much punch. All right, let's add something to this Lagrangian here. Well, let's also add, if all we had was phi dot squared, incidentally, then our equation of motion would be phi double dot is equal to 0. Analogous to, but not the same as phi dot equals 0. In fact, now that these are fermions, we should give them a different name. I should rename everything on this blackboard and call it psi, just so we don't mix up fermions and bosons. Fermions I'll always call psi. Why is it taking longer to just, this is psi dot equals 0. All right. Now I want to put in order to get this side to oscillate, I had to put a restoring force. This was the restoring force, the m squared phi squared. That's what this was doing here. Without it, we would just have phi double dot equals 0. Is there a possibility of making psi oscillate? What do we do to make psi oscillate? To make psi oscillate, we add to the Lagrangian plus m psi squared. Supposing we add plus m psi squared, not m squared, but m times psi squared, similar to this, but with only a single power of m, then what happens? Well, then we will get psi dot equals twice, let's see, do I want to make, I think I just might want to put, there's some 2 in here that I'll want to put in a moment. Psi dot equals minus psi dot. That's what I got from this term here. But what will I get from this term? We'll get plus m psi. In other words, let's go back over it again. Partial of L with respect to psi dot. That's just psi, and d by dt of it, just psi dot. That has to equal the derivative of the Lagrangian with respect to psi dot. That's psi, with respect to psi, that's psi dot, plus m, twice m psi, I guess. Minus sign, why?
Because it's a Grassmann.
What's that?
Because it's a Grassmann number.
Well, no. Actually, psi squared is 0. What you really should do, what we really should be doing is having 2 different psis here to really get it right. Okay. Let's do it more consistently. Let's do it more consistently. Let's put 2 different psis, a psi 1 and a psi 2. It could also be the real and imaginary parts of a complex psi. Let's take the Lagrangian now. Psi 1 dot psi 2 plus psi 2 dot, or plus psi 2 dot psi 1. If these were bosons, this Lagrangian would be completely trivial. All right, let's see why. It's for a similar kind of reason. If these were bosons, supposing we took the equation of motion for psi 2, the equation of motion for psi 2, or for psi 1, partial of L with respect to psi 1 dot is equal to psi 2, and if we differentiate that, we get psi 2 dot. This is the equation for psi 1. And that is equal to, from here, psi 2 dot. In other words, it's again trivial if these were bosonic variables. We would just have psi dot 2 equals psi 2, psi dot 2, and also psi 1 dot is equal to psi 1 dot. It would say nothing. But because when we differentiate with respect to psi 1 over here, there's a sign change, the equation of motion becomes more interesting. Now,
Isn't that just psi as a constant?
yeah, it is just psi as a constant. That's the solution to the equation. It's a differential equation. It has a solution. The solution of psi could be any constant. All right? Now, if we add to this plus m psi 1 psi 2, let's add m psi 1 psi 2 and see what we get. Okay. All right, so let's again take the equation of motion for psi 1. That gives us psi 2 dot. All right. And from here, what do I get from here? Well, let's first do this one from here. That gives us partial, that equals psi 2 dot, differentiating with respect to psi 1, and from here we get plus m psi 2. I think I did that right? Did I do that right?
Is it a minus or a plus?
Differentiating with respect to psi 1. The derivative with respect to psi 1 dot is psi 2, and then you differentiate that with respect to time. That's psi 2 dot. Here we differentiate again with respect to psi 1, but now we get a minus sign because the psi 1 is in the wrong place. We have to push it through to here to differentiate it. That gives us a minus psi 2 dot, excuse me, minus psi 2 dot. What's that?
Euler's equation has minus there.
No, no. No, no. Euler's equation is the L by the, let's call it x dot, is equal, d by dt, is equal to dl by dx. No minus sign from Euler. Right. Psi 2 dot is equal to minus psi 2 dot plus m. Now I'm differentiating with respect to psi 1, so that just gives me psi 2. All right. I think if I were being consistent with standard notation, I would probably put a half here. And then my equation would come out to have a half here, a half here. When I shift this over to the left-hand side, I would just have psi 2 dot is equal to m psi 2. Now what kind of solutions does this have? We need an I somewhere, don't we? Let's put an I over here because an I does belong over here and over here. Plus. Okay, so we would have I psi 2 dot equals m psi 2. Now what kind of solutions does it have? Oscillating. All right, so this is now a fermionic variable which oscillates with time. It has I times d by dt is energy. I d by dt is energy, and so each quanta has energy m. Now, what about psi 1 dot? What happens to psi 1? Well, if you go through with psi 1, will we find the same thing or will we find a minus sign?
A minus sign.
I think we'll find a minus sign. I think.
No, you did it with regards to psi 1, with the first equation.
Yeah, when I differentiate with respect to psi 1, I get an equation of motion for psi 2. Now I want the equation of motion for psi 1 itself with respect to psi 2, and either I'll get a minus sign here or not, I'm not sure. I think I should get a minus sign here if I did it right. Okay, but in each case, it's an oscillation. All right, the interesting point is that the Lagrangian for a Fermi field, instead of having m squared times psi squared, has just m times psi, where m is the frequency, and the kinetic term only has one time derivative. You've seen that before in the Dirac equation. The Dirac equation is a first-order equation in time, whereas the Klein-Gordon equation, which is like this, is second-order in time. Yeah.
It seems to me that this Lagrangian, because they're Grassmann variables, is sensitive to the order that you write psi,
Yes, it is.
psi dot and psi
Yes, it is.
and 2, 1 in.
Yes, it is. Yes, it is. I don't think the physics is, but I think the final physics probably doesn't depend on it. But all right, I just wanted to go through the Lagrangian formulation of this system, and it consists of a Lagrangian which contains phi dot squared over 2 minus m squared phi squared over 2, and then something like, I think there's a half again, psi star, or psi 1, or we can take it to be psi star dot times psi with an I plus psi dot psi star plus m psi star psi. All I've done here was replace psi 1 by psi 2 by psi 1 plus I psi 2 and psi 1 minus I psi 2, and I'll find that I can rewrite it like this. The real and imaginary parts of psi just being what I called psi 1 and psi 2 here. All right, this is basically the Dirac equation in a very, very simple context where there's only one direction of space-time, namely time, just ignoring space altogether. The boson is a harmonic oscillator, and the fermion is just a component, a complex psi field. Okay, now we want to come to supersymmetry. This Lagrangian does have supersymmetry. Let's just review that quickly. This Lagrangian has a symmetry between fermions and bosons. It obviously does. You take out a fermion and you put back in a boson, or vice versa, and you don't change the energy. All right? So there's some kind of operation which takes a fermion to a boson, or removes a fermion, replaces it by a boson, and those are the supergenerators. Those are the Qs. So let's write those out. Q dagger is A dagger A plus, let's just call it A plus, C minus, and just for convenience and notation, let's put a square root of twice the mass here. Since we haven't defined Q dagger yet, I'm free to put any number that I like in front of it. What does it do? It removes a fermion and puts in a boson. The conjugate of it, Q, is just A minus C plus times the square root of 2m. Again, as I said, the square root of 2m is there as a convention, the convention having been established in some other context. Okay, these are the Q operators, and they satisfy an algebra. They have a anti-commutator algebra, not a commutator algebra like angular momentum, but an anti-commutator algebra. Well, it has some pieces which are commuting and some pieces which are anti-commuting. So if I anti-commute Q dagger with Q, we've done that before. I'll tell you what we get. We get twice M, and then A dagger A plus C dagger C. Or A dagger A minus C minus. The dagger and plus are the same thing. Okay, in other words, we get twice the Hamiltonian. We could have made it simpler and just made it 1 times the Hamiltonian if I wouldn't have put the 2 there, but then I would have disagreed with somebody else's notation. And since by now the notations are completely standardized, I put the 2 here so that we would agree with everybody else's notation. This is one fact. What about the anti-commutator of Q dagger with Q dagger? Well, that will have, for example, the product of 2 C pluses. There'll be a C plus from here and a C plus from here. Every term in this anti-commutator will have 2 C minuses, I guess, and C minus squared is just 0. So this is 0, as is anti-commutator of Q with Q. One last thing to do, since on the right-hand side of this algebra we wound up with H, then H somehow belongs with Q in a common algebra, but H is a commuting thing. It's an ordinary number, it's not a Grassmann number. And when you commute or do whatever you do with Grassmanns times ordinary numbers, the rule is commute, not anti-commute. All right, so we could check one last thing. We could check what's the commutator of Q and Q dagger. I'll just write Q dagger, but it's the same for Q, with H. And this is easy to work out. I leave it as a homework assignment to work out the algebra of it. The algebra of it is a couple of lines. What's the answer?
Q.
Q?
No, it's 0.
0. It's 0. It's 0. If there was just an A by itself, then the commutator would have an A. If there was just a C by itself, the commutator would have a C. But with both of them there, the commutator is equal to 0. Check that. Check that for yourselves.
We actually wrote it on the board.
I did? Here, it's on the board.
No, a few weeks ago.
Oh, we worked out the commutator?
Yeah.
Yeah. Okay, well, the commutator is 0, and that has an implication. It has an implication as obscure as whatever Q is. And Q is an obscure thing. It's a Grassmann variable, or it's got a fermionic character to it. When you measure it, well, you don't measure it. But what does it mean to commute with a Hamiltonian? Well, it first of all means a symmetry. But it also means, that there's some symmetry in the system, in this particular case, taking out a boson and putting in a fermion. But also, it means that Q's are conserved quantities. They're conserved quantities. They don't change with time. And so you can label states by their values. Labels in the same way that you label them with energies or charge or other things. These are called supercharges, incidentally. They're called supercharges because they're conserved quantities. Super, I don't know why, but charge, like electric charge, it's conserved. That's the important thing about it, it's conserved. All right, so there's this algebra of commutators and anti-commutators. Of course, there's one more, which is a stupid one. It's just that the commutator of H with H is also equal to 0. Everything commutes with itself. And so we have a closed algebra of a set of variables, H and Q. Now, there's another way of thinking about supersymmetry, and it's by adding dimensions to space-time, Grassmann dimensions. So let's go through that again. Remember that things like Hamiltonians and momenta, now I'm adding back in position for a moment, just temporarily for a moment, spatial position. A Hamiltonian is represented in quantum mechanics as I times the derivative with respect to time. So for example, the Schrodinger equation says H on psi is equal to something. It becomes an equation for the time derivative of the wave function. So H is I d by dt. What about momentum? Minus I d by dx. So very often, very, very often, in fact almost always, it's the case that symmetry generators are related to derivatives with respect to some kind of variables. What about angular momentum? Angular momentum, which rotates space, is related to various combinations of x and d by dx. They're related to differential operators, namely the differential operators which just rotate you a little bit. So when we look at these Q's, you might ask, are they related to some sort of differential operators, but not derivatives with respect to t or x, but derivatives with respect to theta? Why? These are Grassmann numbers after all. And so if they're Grassmann numbers and they have to do with symmetries, they should have to do with symmetries of coordinates which are Grassmann numbers themselves. So I think we wrote down the last time the representation. We add a complex dimension to time, t and theta. Theta, or we can also add theta is a complex Grassmann variable. We can put in theta bar also, the complex conjugate of it. I will interchangeably use the notation bar and complex conjugate. It means the same thing. So our degrees of freedom depend on t and these Grassmann coordinates. Okay? A very, very obscure and odd thing to have invented, but let's do it. Let's see what it means. Okay, so now we'll write, first of all, q dagger is equal to derivative with respect to theta bar. It's possible that I'm changing notation relative to last time. I don't remember. D by d theta bar minus I theta d by dt. And q, now here I know that I had a mistake the other day because somebody pointed it out to me, is d by d theta. And I think the last time around I wrote plus I theta bar d by dt. But that was wrong. Did I write minus? Then why did somebody come up afterwards and say that they...
Because it worked out for them. It works out if you have two pluses.
No, the first one, I think the first one was plus and the second was minus. They were different signs.
No,
Which
you
way did I
write
have it
the-
last time?
No, you had minus then plus, and I think it works out if you do plus and plus.
Yeah, well, it'll also work out with minus and minus. I assure you of that. Yeah, it'll also work out with minus and minus. The usual notation, look, part of it is convention. Part of it is convention. Part of it is convention. But the fact that these two signs should be the same, that's dictated by these commutation relations, these anti-commutation relations. These signs should be the same. Now, it looks funny. This is the complex conjugate of this. You might think you should have changed the sign of I here. But go back a step. Remember that in quantum mechanics, things which are real correspond to things which are Hermitian and observable. Remember the fact that momentum is equal to minus I d by dx? That's a little bit peculiar, isn't it? Because momentum is a real quantity, and so the right-hand side had better be a Hermitian operator. And the answer is that d by dx is not a Hermitian operator. I times d by dx is a Hermitian operator. You can work that out. We've done that in the past. I'm not going to work it out now. When you see a differential operator like d by dx, think of it as pure imaginary. It's pure imaginary. It is not real. The thing which is, or the real differential operator is minus I d by dx. All right, so I d by dt is thought of as real, and when you complex conjugate it, you don't change its sign. That's a thing that I got wrong last time. Both these signs should be the same. Now if you anti-commute them, where does the anti-commutator come from? The anti-commutator comes when you anti-commute these, you'll have an anti-commutator of d by d theta with theta, d by d theta bar with theta bar. What's that anti-commutator? It's 1. So it'll give you a I d by dt. And the other way also will give you an I d by dt. I'm wondering now if I do really need the sign to be, yeah, I think.
Yeah, the p commutator vanishes. The p bar commutator vanishes. So the first and fourth terms go away, right? The non-cross terms.
Yeah, these commute with each other, or anti-commute with each other. These anti-commute with each other. And these here, no, I think it's minus. I think it really is minus. Yeah, so it must be plus. It's either plus or minus. I thought, I worked it out at home and I got minus. And now that I see it in front of me, I d by dt is h. Yeah, okay. All right, I guess it's plus. My mistake. In any case, you will get a 2h here. The 2, where does the 2 come from? The 2 comes from the two terms, the anti-commutator of d by d theta bar with theta bar, and the anti-commutator of d by d theta with theta. So when you anti-commute these, you'll get exactly twice twice I d by dt. This d by dt will just stand there on the right. Okay, and I d by dt is h up here. All right, so that's the basic algebra of this very, very simple supersymmetric system. All right, the next thing is to introduce fields. Now, in the world that we're considering now, there's only one dimension of space-time, and it's only time. We're going to come back and put in space. It'll make complexity and make it more complicated than this. But until we put in space, there's only one dimension of time. You know, physicists are constantly thinking of multi-dimensional spaces. They think of four-dimensional space-time, which has one dimension of time and 3 dimensions of space. They think of 10-dimensional space-time, which has 1 dimension of time, 9 dimensions of space. We sometimes think of 5 dimensions. It's called Kaluza-Klein theory. 4 dimensions of space, 1 dimension of time. We even think about 1-dimensional space-time, which has 1 dimension of time and no dimensions of space. And that's what we're doing here, just for simplicity, just to see how the machinery works. All right, so now we should introduce a field. And that field should depend on time and the thetas. Well, that's all there is that's time and the thetas. So let's call the field capital Phi. It is not this phi over here. That phi is small phi. This phi, big phi, is a superfield. It's a superfield, which means it depends on time and the thetas. Let's write out all possible expressions that could go into it. I'm going to assume that phi is a bosonic object. In other words, that it's an ordinary number. That means the first term, which contains no thetas, is an ordinary field, and it could be this field right over here. Function of time. Then we can have things proportional to theta bar. Theta bar times psi. Psi is a fermionic variable. Theta is a Grassmann variable, or theta bar is a Grassmann variable. And then we can have psi bar times theta. And the last thing we can have is what I will call d theta bar theta. What comes after theta bar theta? Well, you could have theta squared times theta bar, but that's 0. You could have theta times theta bar squared, that's 0. You can't have more powers than just theta times theta bar. So it terminates there. That's it. That's the general dependence of a superfield in this context, in this very simple quantum mechanics context, or this very simple one-dimensional world. A function of time. Of course, these are also functions of time. And d is also a function of time. But this is the general expansion. Okay. That's now, what do these supersymmetric transformations do when they act on phi? What does an ordinary transformation, like t goes to like a shift of t do? A shift of t just takes phi to phi of t plus a shifted value of t. What does a supersymmetry transformation do? It's a coordinate. It's a coordinate transformation on the t theta theta bar set of axes. That's all it is. It's a coordinate transformation. But here I'm going to write down what it is, and then I'll show you that it really does agree with these things here. It is the transformation t goes to t. Now I'm going to introduce a new Grassmann number. The new Grassmann number will be called psi, and it also has a conjugate. Let me tell you what I'm doing in another form. What I'm imagining doing that you ordinarily might do in space, ordinarily space, you might shift the coordinate x by writing x goes to x plus a small shift epsilon. Okay? That's a coordinate transformation you might do, which would just shift your x-axis. epsilon would be a parameter of the transformation. Now what we're doing, all right, let me say, what we're doing now is we're shifting theta. Theta goes to theta plus a Grassmann number psi. Theta bar goes to theta bar plus the conjugate Grassmann number theta bar. So they're shifts, they're translations of the theta axes, that's all, just translations in theta space. But at the same time, you translate time. But how much do you translate time by? Time goes to t plus or minus t minus I c bar theta minus I c theta bar. I will not swear to the signs because I worked them out and they seem to change. They seem to have this magical way of changing between, and my drive over from home to get here, the signs sort of seem to change on the paper, and I don't know why. It must be, oh, when I commute to work, the signs change. Why didn't I think of that? I don't know.
What is the D again?
What is what?
On the top, the big.
D?
Yeah, D of T.
D is just another variable. It's just the power series, it's just the coefficients. If phi is a function of t, theta and theta bar, we can expand it in the power series expansion in powers of theta and theta bar. We could also expand it in powers of t, but that would not be a useful thing to do. We just leave it as a function of t, but expand it in powers of theta bar, theta, theta bar, theta, and that's it. Can't go any further than that. All right, so that's the most general function of theta and theta bar with a t dependence in each one of its places here. Now what does that mean? That means that the system contains a boson variable, fermion variables in their complex conjugate, and it appears like another boson variable. It appears that there's another boson. It appears there are two boson variables. But in fact, we're going to find that's not the case. We're going to find that something, I think the reason D is called D is D for dummy, a dummy variable. I didn't invent the terminology, and I'm not sure why it's called D. Okay, so now this is the field. What do we need to have a field equation? We need an action. Okay, we need an action. So I'm going to tell you now how you build actions. You build actions by building up various kinds of products, derivatives, and so forth of fields, and you make a Lagrangian. And then you integrate the Lagrangian over position, over time, to make an action. You integrate the action. What do you do in ordinary field theory? You integrate the action over time and space. Here, we will integrate the action over t and theta bar. We're just going to more or less think of theta and theta bar as ordinary coordinates. I think we're finished here. And write an action. The action is going to contain various kinds of expressions involving capital phi here and its derivatives. Okay. Just as we would do if theta and theta bar were ordinary coordinates. All right, so we're going to have an action. And the action is going to be an integral dt, an integral d theta, an integral d theta bar of some, let's call it lambda. I don't want to call it an ordinary Lagrangian. It's super Lagrangian. Let's call it lambda instead of L. Normally I would use L for Lagrangian. The term Lagrangian would not be used for this thing. We'll call it capital lambda, the super Lagrangian. And the super Lagrangian is itself a superfield like this, but it may be, for example, it might contain the square of superfields, it might contain all kinds of derivatives of superfields and so forth. So whatever it is, the Lagrangian itself might have a similar expansion in powers of no theta, theta bar, theta, and theta bar theta. That's all it can have. The Lagrangian here is a function of t, theta, and theta bar. Now, we have to integrate over theta, keeping in mind that this lambda contains various terms. Let's call it lambda 1 plus, well, it'll have various terms of exactly the same kind. The first term will be bosonic. The second term will have a theta bar times a fermion. The third term will have times a fermion, and the fourth term will have theta, theta bar. But what goes here may be more complicated. It won't just be a simple field. It'll contain time derivatives, quadratic things, all sorts of stuff. All right. What happens when you integrate a function, theta, theta bar, when you integrate a function with respect to theta and theta bar? Did I tell you last time how to integrate over thetas? Yeah. What happens? It is the same as differentiation. You get the last term. No, not the constant term. You get the last term, the one which contains the maximum number of thetas and theta bars. And that's all you get. So whatever this Lagrangian is, this part of it just picks out the last term, which is proportional to theta bar theta. It's called the d term of the Lagrangian, although it is not necessarily just the d term in this expression here. It's the last term. It's called a d term, but without naming it, it's just the last term. In fact, we can call it lambda theta bar theta. The last term in the expansion of lambda, integral dt. In other words, whatever the last term in lambda is, it's just the ordinary Lagrangian. The ordinary Lagrangian is a thing that we integrate with time, having never heard of thetas and theta bars. And whatever this last term is here, it's just going to be what we can redefine to be the ordinary Lagrangian. So supersymmetric theories have super Lagrangians, which go into an expression like this. But they also have ordinary Lagrangians, which are just the last term in this expansion here. The trick is to keep the system invariant under the supersymmetry transformations. In other words, to make sure that the symmetry is preserved. And that's a trick that we're going to discuss. Okay, so we need to know how to build various kinds of expressions out of the superfield. We need to know how to build expressions which involve derivatives, which involve higher powers of the field, exactly the things that we might do if we had an ordinary field and we wanted to build a Lagrangian. We would differentiate phi, square the derivatives, we would multiply higher powers of phi, all the usual things we do to build an interesting Lagrangian. We're going to try to do, and we're going to succeed, we're going to try to do for phi here. Okay. Before we do that, I know what we missed. What I didn't show you is that these transformations here are the things which are generated by these Qs. I didn't tell you what the connection between this transformations and this was. Did I tell you?
Oh, you did derive that, yeah.
All right, we did derive it, but let's just go back through it again. If we have a superfield like this, and we shift the arguments a little bit, what happens to the superfield? What's the change in the superfield? Let's write the change in the superfield if we make these changes. This is the change in the superfield. All right. First of all, this one says shift theta a little bit. So that says shift theta, differentiate the superfield with respect to theta, and then multiply that by psi, like that. We've shifted theta by amount psi. The change in the field is the derivative with respect to theta times psi. Now we've also shifted theta bar plus the derivative of phi with respect to theta bar times xi bar, I think. Yeah. And last, we're shifting the time variable a little bit. So what do I do when I shift the time variable a little bit? I take a time derivative, right? Take a time derivative plus phi dot times the amount by which I shift phi, by the amount by which I shift t. So that will give me a phi dot times minus I psi theta bar minus I xi bar theta, I believe. That's what happens. That's the small change in phi when I make such a transformation. Simultaneous transformation of theta, theta bar, and t. That's how phi shifts. Now let's collect together the pieces that multiply psi. That's d phi by d theta, and also phi dot times xi times theta. Let's see, the pieces which multiply xi. Here it is, xi equals xi times d by d theta. I'm going to put q out, I'm going to put phi out here in a minute. Phi out here. We first differentiate with respect to theta, and then where's the other piece? What have I done here? This should be minus. Multiplies, right? Multiplies, yeah. Okay. D by d theta. Now, what's the other thing that multiplies psi? It is minus I xi bar. I got the xi outside. Times d by dt. All times theta. Oops, nope, there's a theta bar. Theta bar. Now, apart from that nuisance little sign that for some reason or another I seem to have wrong. It is just.
Yeah, in order to hit it with a derivative, you're going to need to move the theta past the epsilon, past the xi. So.
I don't think that's what's wrong. No.
No,
The xi is a Gauss,
I'm not differentiating it. This is it.
xi is a Grassmann number, right? So you got to bring the
C
theta,
is a Grassmann number.
right? And you got to bring the theta bar over.
Why? I don't have to. In fact, I don't want to. I want to leave it this way. Yeah, I want to leave it this way. Then there's another term, incidentally. The other term is sort of the complex conjugate with xi bar times similar stuff times phi. Well, I seem to have some systematic trouble with
No, but don't you have the phi outside, right? On the right hand side?
Yeah, here.
But here you had it on the left hand side, so you got to take it across, right?
No.
See, I think this is where your plus sign comes in, because when you take the time derivative, the I goes in the denominator.
I goes in the denominator.
Yeah, see, your change is plus I, but the d by dt is going to put the change of t in the denominator, right?
No. No. This is just partial derivative with respect to time.
No, I'm saying that you have t goes to t plus something, minus something, okay,
Right.
minus I something.
Yeah.
And that's going, in the d by dt expression, it's going to be in the
No.
denominator
When you
of that.
shift the argument of a function a little bit, you just differentiate with respect to the thing that you're shifting and multiply it by the amount that you've shifted the argument by. All right? Now, there's a very simple cure to this. The reason that I wrote minus here was because I was tracking some sign conventions that I had inconsistent back over here someplace. I don't know where. Someplace over here I had some sign convention inconsistent. And yeah, I'm fuzzy about the signs, and that's my problem with this subject. I can never keep track of the signs. They come and they go, and I can't keep track of them. All right. In any case, a consistent set of signs would probably have to have a plus here, and then it must be plus over here. Okay, so what is this thing here inside the bracket? What is that differential operator inside the bracket? It's just Q. So this is Xi times the differential operator Q, and then from here, plus Xi bar times Q bar, acting on phi. And remember what these things are? These are derivatives and various kinds of differential operators. And you simply work it through. You simply take these derivatives, act on phi. Phi, when you want to differentiate with respect to the thetas, it's straightforward. You just, only thing, you have to keep track of the signs. And that's what these Q's are. They're like momentum. They're like momentum, but not for shifts of x, but for shifts of these thetas, simultaneously shifting time in this way. That's the basic symmetry that's called supersymmetry. It's a kind of shift symmetry in these Grassmann coordinates, but not just a shift symmetry. If it was just a shift symmetry in the Grassmann coordinates, then there would only be these d by d thetas and the d by d theta bars. There would be no I theta d by dt and so forth. All right, so then you would just have these terms. What would be the anti-commutator of a Q with a Q dagger if there was only d by d thetas? 0. 0. So it would not satisfy this algebra. Where the devil is the algebra? Who knows? I've lost it by now. Yeah. You would not have the right-hand side containing the energy. It would not represent the algebra that we started with. Now, the algebra we started with was very simple. We're making something fairly simple into something fairly complicated, into a complicated story. But you can see the story is kind of interesting. It's saying that the basic symmetry can be thought of as a geometric symmetry of shifting and translating in this space, which now contains not only time, but also theta and theta bar.
I think you had mentioned at some point that there was a backwards in time element. That may be where you had the minus sign.
Possibly. Yeah, I don't know what happened to the sign. Yeah.
Is there any physical realization of the extended definition of time that you have here?
Well,
Or is it really just a bookkeeping?
it really just, it's just a bookkeeping, from one point of view, it's just a bookkeeping device that keeps track of this simple algebra here. The reason that it is important to go this route here, this more complicated route here, is because we're going to want to make Lagrangians and systems which are more complicated than just harmonic oscillators interacting with size or not interacting with size. This is a very simple system up there, harmonic oscillator and CC dagger and nothing else. There's no interactions. The particles don't interact with each other. They don't scatter off each other. They don't do anything. To have something interesting happen, we have to make more complicated Lagrangians. And the question is, how do you make Lagrangians that at every stage preserve the supersymmetry? In other words, which preserve that at every stage the bosons and the fermions are going to have exactly the same mass. That's not obvious how to do. How do we do it in relativistic physics? How do we make sure that our dynamics is relativistically invariant or translation invariant or whatever? Well, we write Lagrangians and we make sure that the Lagrangians have the symmetries that we want. So when we're doing Lorentz invariants, we invent vectors and tensors and all these objects. We have a whole tensor algebra, and we build out of all of the objects of the theory, we build scalars. The Lagrangian has to be a scalar. If the Lagrangian is a scalar, if it's made up, it can be made up out of vectors, tensors, all kinds of things, derivatives of vectors, derivatives of tensors. If the Lagrangian is a scalar, the theory will be invariant under Lorentz transformation. We're trying to do, and not only trying to do, we will succeed in doing it, but it's much more abstract. Basically constructing the methods of producing invariant Lagrangians. Invariant under what? Invariant under these new kinds of transformations, which contain shifts of theta and translations of time. So that's the goal, to have a calculus of constructing invariant quantities, and in particular invariant Lagrangians. And those Lagrangians may be much, much more complicated than that simple free field. That's a free field, no interaction between the fermions and the bosons. How would you construct something where the fermions and the bosons interacted? That you need this machinery for. You need machinery like this to know how to do that. Okay, so let's talk about that machinery a little bit. What can you do with a superfield to make another superfield? One of the things you can do is square it. You can square a superfield. Let's go through the exercise of squaring the superfield, and that makes another superfield. So let's just take, we have phi. Phi is equal to, where is it? It's over here. Let's write it out. It's equal to phi plus theta bar psi plus psi bar theta plus d times theta bar theta. Do I have it right? Yeah. Okay. Now I want to square it. The best way to square a thing is to write down another version of it. And okay, let's phi squared, phi times phi, which is just phi squared. I wrote it as phi times phi, just phi squared. All right, so let's see what it contains. Well, it will contain the bosonic variable phi squared, the ordinary number squared. Okay, then it will contain phi. It will contain a term with theta bar plus theta bar times phi psi. Then it will contain plus a theta term, phi psi bar theta. And now last from this term, it'll contain phi d theta bar theta, right? That's the first term I get when I multiply this through. Now, next one, multiply this by this. And what will we get? We will get theta bar phi psi. In other words, I'll just get this times this is the same as this one times that one. Is that right? Yeah. That one again. Now I will get this times this. That will give me theta bar theta. That will give me, let's put it over here, theta bar psi bar theta. That's this times this. And what about the last term over here? 0, because it contains theta bar times theta bar. Now, next, we have this times this. That looks exactly like this here. That's plus phi psi bar theta. This one times this one. Then we have psi bar theta plus psi bar theta theta bar psi. That's this one times this one. This product gives 0. 2 thetas, and this one also gives 0. And there's only one more term. The last term is plus d. No, yeah, let's see. Yeah, there's only one last term. It's d times phi times theta bar theta. That's it. All the other terms are 0. There's nothing else besides that. And now we can add them up. This combines with this to give a factor of 2. This combines with this to give a factor of 2. And then we have all these last terms here with theta bar theta. Let's see what there is. There is phi times d and d times phi. Phi and d commute with each other, so there's just a factor of 2. Phi d theta bar theta. Get rid of this. And here we have another theta bar theta. Let's bring this theta bar theta through here, past here, and then past here. Do I actually have the signs right? I can't tell. I do not know. I can't tell. If it's worked out, this one should have the same sign as this one. So let's bring theta bar through. If you bring theta bar through 2 variables, it doesn't change sign. So this will be plus theta bar theta. Oh, I know what. Yeah, I want to now I'm going to. I always like, for reasons that have nothing to do with anything, I always like to keep the bars on the left. And it's just a way of keeping a mnemonic for me. So I always like to put the bars to the left. So if I put the bar on the left here, that will change the sign. All right, that looks nice now. Now I believe that. Now, what about this one over here? All I want to do is bring psi through till it's over here, but then shift theta and theta bar. That's going to give another sign. It's just going to give twice this. Okay. Here's phi squared. Now, what do I want to do with phi squared? It might be a thing that I would want to put in a Lagrangian. Why not? It's a perfectly good superfield, phi squared, and I told you before that we're going to build up our Lagrangian, or our super Lagrangian, out of powers of phi, derivatives of phi, and so forth. All right, so this might be a thing in a Lagrangian. What would I do with it then? In other words, it could be part of lambda. Maybe not the whole thing, but part of lambda. Good. It's part of lambda. What do I do with it? I integrate it d theta bar to find the ordinary Lagrangian. In other words, I pick out the last term. Remember, integrating over theta and theta bar is just picking out the last term which contains theta and theta bar. All this work just to pick out the last term here. So if I put this into the Lagrangian, what it would give me would just be twice phi d minus, I guess, twice psi bar psi. That would go into a Lagrangian that would be guaranteed to be supersymmetric because it was built up out of a superfield which had a characteristic distinct transformation under the supersymmetry transformations. All right, so this is the way you build up Lagrangians. Now, this is not a very interesting Lagrangian. What does it have? Phi times d, we don't know what d is, and psi bar psi, it has no time derivatives. Hasn't got any time derivatives. We'd like to put in something like a kinetic term to get some time derivatives. So what we have to know is how to build derivatives of superfields. How to build derivatives of superfields. You might think, well, just time differentiate them. That's not the right way, because when you time differentiate a superfield, you don't get another superfield. So you have to be more careful in that. getting exhausted? No. Really? I am. Okay, so we have to know now we've figured out how to build powers of superfields. Incidentally, there would be nothing to stop us from writing phi cubed or phi fourth or phi anything else. It's a little exercise. Take phi cubed and pick out the last term. See what you get. What you're going to get is various things with phi squared d. You're going to get things with psi bar psi times phi. But it's an interesting exercise to try, in fact, to take phi to the nth power, and see what the last term is. There's a rule, and the rule, I'll let you try to work it out. For the nth power, I don't want to compute the whole nth power. All we want to do is pull out the last term, the theta bar theta term, and that'll be a term, an interesting term, candidate for a term in Lagrangian. Okay, now, what about derivatives? Derivatives are subtle. I want to define a constraint on a superfield which preserves the fact that it's supersymmetric, that it has supersymmetry. I'll tell you what I'm thinking about. Let's suppose we were talking about ordinary space. Ordinary space, we might have two coordinates, x and y. I might say, I'm interested in, I'm thinking to myself, I really don't have a field which is a function of two coordinates. I really have a field which is a function of only one coordinate or one combination of the coordinates. For example, it might be a function only of x squared plus y squared, or it might be only a function of x, or it might only be a function of y. In other words, it might satisfy some rule such as the derivative of the function or the field, whatever it is, with respect to y is equal to 0. Now, that's a kind of stupid thing. It says that f is only a function of x. Why did I introduce a y dependence in the first place? Well, never mind, but I might be interested in fields which only depend on y. Now, supposing the theory that I was considering was rotationally invariant, would it make sense to say, let me only choose those functions of y, only those functions of position as possible fields which are independent of y? Of course not, because if a theory is rotationally invariant, a thing which only depends on x, when you rotate it, will suddenly have some y dependence. So this would not be a rotationally invariant constraint. It would not make sense to say, let's only think of fields which satisfied derivative of f with respect to y is equal to 0. Why not? Because it can't be rotationally invariant. And if the physics we're trying to imagine is rotationally invariant, that's one way of saying it. Another way of saying it is if I apply this constraint, let's give a name to this. Let's call fields which satisfy this constraint, let's call them, what shall I call them? Magic fields. Okay. These are magic fields here. Now, or f is a magic field. If f satisfies this, by definition, it's a magic field. Okay, now let's rotate coordinates. In other words, let's apply a rotation in the form of an infinitesimal generator, for example, to f. We rotate f by acting with the angular rotation generators, L, on f. That just corresponds to a rotation, a small rotation of f, whatever it is. Is L times f still, is rotating the field still a magic field? Is the result of rotating the field? In other words, what we're doing actually is writing a small change in f. We're writing, rotate the field. The change in f is equal to, I suppose, I times L times f. where L is the angular momentum generator of some kind of derivative, just a derivative which rotates things a little bit. All right? Will delta F also be a magic field? No, it won't. No, it won't. And the reason is, if you take a thing which doesn't depend on y, but does depend on x, and rotate it, it no longer satisfies that same constraint. Now, what's a way of doing this mathematically? We'll do let's call this constraint, let's call it d. D for derivative with respect to y. Let's just call it dy equals 0. This defines being magic. All right? Let's ask whether f plus delta f is magic. So the question is whether d is also equal to 0. Well, delta f is just proportional. D times f, that's 0. By definition, f is magic. All right? But what about d times delta f? And delta f is proportional to L times f. Is that magic? Well, there would be one thing which would assure that L times f was still magic. It would be that L commutes with d. Supposing L commuted with d, then we would say this was L df, and we've already assumed that d times f is equal to 0. The only problem here is that it's just not true that d commutes with L. L is a rotation, is a generator of rotation. D is a derivative along the y-axis. And when you rotate, or when you commute, what do you do? What do you get when you commute a derivative with respect to y with a rotation? Do you know? A derivative with respect to x. Remember what an L is. An L is an infinitesimal rotation. What does it do? It rotates the components of vectors. Right? It rotates the x component of vector into a y component of vector. If you commute the rotation generator with the translation generator, you just get the rotation generator in the other direction. That's what you get. So these don't commute, but the test for whether a constraint, here's the question, is a constraint like this consistent with a symmetry? Is imposing a constraint on a field consistent with a symmetry? It's consistent with a symmetry when the constraint commutes with the symmetry generators. All right? That's the test. Does the constraint commute with the symmetry generators? Okay, so let's now ask, does the symmetry generators in the case we're interested in are the Q's? Where did the Q's go? The Q's are gone off the blackboard somewhere. Have them where? Yeah, okay, right. We have the Q's, not in the blackboard space. We have the Q's. For example, Q, I think, is equal to d by d theta plus, did we say, I theta bar d by dt? Yeah. And Q bar is equal to d theta bar plus I theta d by dt. Okay. Let's see if we can build up some kind of derivative. I'm just going to tell you the answer. It's a very simple answer. For a derivative, and I'm going to call it capital D, just call it capital D, it's going to start with d by d theta. It's basically derivative with respect to theta, but not quite, because d by d theta does not commute with q bar. d by d theta does not commute with, it does not commute with this term here, or anti-commute. We're interested in asking whether we can find a d which anti-commutes with q and q bar. That's the analog of commuting in ordinary algebra. Is there a d which is a kind of derivative with respect to theta, but which has the property that it commutes with both q and q bar? If it does, then it's a candidate for something which allows us to define a constraint which is invariant under the q's and q bars. Okay, so does d by d theta commute with q and q bar? No, it doesn't commute with this term here. Can I add anything to it to make it commute? Well, the natural thing to try to add to it is something like appears here. Well, let's try plus I theta bar d by dt. That's not going to work because we know this is just q, and q doesn't anti-commute with q bar. But what happens if I put a minus sign here? I'll let you work it out.
Okay.
I'll let you work it out. The answer is it commutes with both of them. I think you checked that. Isn't that what you had checked?
Yes,
Yeah.
that was the problem.
That was the problem, right. I had misidentified one of these and called it this. Yeah, it's a nice check to prove that this D anti-commutes with both Q and Q bar. So does D bar.
It's particularly useful that we established that the commutator of theta with d by d theta,
The anti-commutator.
yes, the
Anti-commutator. theta-
anti-commutator
Yeah.
is, what was it, 1.
Yeah. Okay. Yes.
Yeah.
Okay. Let's look and see whether this commutes with Q. Does D commute with Q? Well, d by d theta commutes with d by d theta. Anti-commutes. When I say commutes, I mean anti-commutes. d by d theta anti-commutes with d by d theta. d by d theta anti-commutes with theta bar. Theta bar anti-commutes with theta, and theta bar anti-commutes with theta bar. So this one anti-commutes with this one trivially. That's trivial. But now we have to check, does this anti-commute with Q bar? And that's a little bit more non-trivial. You have an anti-commutator from here, d by d theta with theta, but then you also have an anti-commutator from here. And they cancel. They cancel. So whatever d and d bar are, they commute with both q and q bar. What does that mean? That means that the constraint, that if I say, let's consider superfields which have the property that d bar, not both of them is too strong a constraint, that d bar on the superfield is equal to 0. This says that in some way the field is constrained when you differentiate it with this kind of derivative here, it doesn't change. That's a constraint. First question, supposing we change phi by a supersymmetry transformation. Delta phi contains things like q phi and q bar phi. It contains things like q phi and q bar phi. Is the change in phi, does it also satisfy this constraint? And the answer is yes. Let's see why. If we assume that d bar on phi is equal to 0, then let's try to find out whether d bar q phi, is that equal to 0? Question mark. We've made a little shift in phi by applying q to it. And now we want to, let's say that if d bar phi is equal to 0, we could give it the name magic, but it actually has a name. It's called chiral. A superfield which satisfies this constraint is called a chiral superfield. It's the analog of the magic constraint that we talked about before. But let's find out, is this magic constraint or chiral constraint, is it something that survives after you make a little supersymmetry transformation. If not, then we throw away this constraint. All right, so let's see whether d bar, whether q times phi is magic or chiral. Well, the answer is easy. If d bar phi is equal to 0, and if q anti-commutes with d bar, which we proved over here, we can rewrite this as minus q d bar phi. And that does equal to zero because we assumed that d bar times phi is equal to 0. So if phi is chiral, then the small shift of it, when you rotate it or when you shift it by the supersymmetry transformation, is still chiral. Well, that's a good sign. It says, what it says basically is that this is an invariant thing to impose. It's invariant not under anything you can think of, but under the supersymmetry transformations. Imposing this on a field is an allowable thing to do. Supersymmetry doesn't get in your way. It doesn't, a supersymmetric transformation on Q doesn't violate this constraint. That's the fact. Okay, so there we are. That is the notion of a chiral superfield. Okay. We are plunging deep into the morass. We're going to do it. We're going to go for the whole thing. Okay. So let's consider then a chiral superfield that satisfies d bar equals 0. Right. That turns out to say something, well, let's see, well, how should we do this? There's an easy way to construct phis which satisfy this constraint here. It's kind of neat. I'll show you how it works. Supposing this was just d by d theta bar on phi is equal to 0. It's not. But supposing it only contained this term here, it was equal to 0. What would that say? That would just say that phi is independent of theta bar. It would say that phi has the form phi plus theta times, let's call it theta times, or psi bar times theta. But then nothing else, because everything else would have theta bars. So if d by d theta bar on phi was equal to 0, it would be an enormous simplification of the superfield. It would say it contains only two terms, a phi and a psi bar times theta, nothing else. Okay, but that's not what we're doing. That's not what we're doing. This d bar is more complicated. But nevertheless, this is almost right. So let me tell you what's right. You're right that phi is equal, not t, but let's call it tau. And theta. Phi is a function only of tau in theta. But what is tau? Tau is a new thing. It's not time. It's not the original time. Tau is time plus, I think it's plus I theta bar theta. What a weird thing to do. Shift time by an amount I theta bar theta and write that a field only depends on tau and theta. This is like saying that the field only depended on one combination of coordinates. It only depends on tau, which is t plus I theta bar theta, and theta, but not theta bar separately. It only depends on theta bar through this combination. Let's prove that any field of this type, in other words, it's a phi of t plus I theta bar theta and theta. Let's prove that it satisfies this relationship here. Okay. Well, d bar this relationship. D bar is I d by d theta bar, okay? Where do we, it starts with d by d theta bar, and then it has a minus I theta d by dt. What happens when you differentiate this with respect to theta bar? Differentiating this with respect to theta bar gives us, the only place we see theta bar is together with t here. So that gives us plus I think it's minus I, theta d phi by dt. When you differentiate with respect to theta bar here, it's equivalent to differentiating with respect to time and then multiplying by I theta. That's the derivative with respect to theta bar. Now, what about the derivative with respect to time? That also gives you a time derivative and also multiplies by theta, but with the opposite sign. So, any function of this form here, which only depends on theta bar in the special way here, satisfies d bar on it is equal to 0. It's another way, saying d bar is equal to 0 is another way of saying that phi only depends on theta bar in this very, very special way. Okay. Well, that then solves our problem. We can start with any phi which only depends on tau and theta, and then later on, just remember that tau is the shifted value of time. So what is this? This is phi of t plus psi of tau plus psi bar of tau theta and nothing more. We just have to remember that t is not tau, that we have to shift tau a little bit. This is getting
Is that the only formulation that satisfies the constraint?
Yeah. Okay, so this is the form of a chiral superfield. Now let's work it out in detail. Let's work it out in its full ugly glory. In its full ugly glory, let's just remember what tau is. Tau is t plus I theta bar theta. All right, let's start with this one over here. That starts out as phi of t, but then we shift theta bar a little bit, so we have to put in plus I theta bar theta times phi dot. We're just doing a Taylor expansion in the shift here. We've shifted by amount I theta bar theta, so that's phi, plus I theta bar theta times phi dot. And then what would be the next term? The next term, I guess, would be 1/2 I squared, which is minus 1, minus 1/2 theta bar.
You're expanding out the phi of tau? And then you're expanding out the phi of tau plus the...
Yeah, this is phi of, oh boy. Yeah, I'm just substituting, I want to substitute in here tau plus I theta bar theta. Yeah. Then there's no higher term because theta bar theta squared is 0. Theta bar theta times theta bar theta is 0. I guess that's true. And then we have plus psi bar of t times theta, but then we also have to differentiate psi bar plus psi bar dot of t times theta bar theta theta, but that's 0. Theta bar theta times theta is 0, so that's 0. That's the whole thing. A chiral superfield is just a phi and a psi combined together, plus an extra term here which has theta bar theta in it coming from this shift. That's all a chiral superfield is. Now, it seems like a very heavy machinery to do some fairly simple things. This is what the chiral superfield is. What can we do with it? Well, basically, we can square it or multiply it by its complex conjugate and use it in a Lagrangian. Let's see what kind of things would happen if we squared it and put it into a Lagrangian. Okay? So we want to, well, square it means multiply it by its complex conjugate. In other words, we have d bar phi equals 0. Here's phi. Let's multiply it by its complex conjugate. That will make another chiral superfield, multiply them together, and then integrate them with d theta bar. So I think all we have to do is write this down next to its complex conjugate. Phi star of t, if phi is complex, typically now phi is complex, plus I theta bar theta times phi star dot, then plus psi of t theta bar.
On the middle term, wouldn't you do theta bar? Could you do in the conjugate?
Maybe. I'm really too tired to figure it out now. And I'm not recognizing it, frankly. It doesn't look right. I think I'm going to have to stop here and repair my notes. D5 times.
Can you tell us the punchline yet?
Yeah.
What do we do?
Yeah, the punchline is if you do it right and you take d phi and d bar phi, multiply them together and integrate them over theta and theta bar, you will get this Lagrangian. That's the punchline. Yeah. But I think I better do it over next time. This is more than one lecture's worth, and I've run out of steam. The point is, look, let's say what the point is. The point is to build supersymmetric Lagrangians. Lagrangians, what is a supersymmetric Lagrangian? It's one which has this fantastic symmetry that you can replace bosons by fermions, and that in fact means that it guarantees that fermions and bosons come in matched multiplets with exactly the same mass and will do exactly these things which we required of a Lagrangian, which will cancel all, if it comes in matched fermion-boson pairs, then you can prove all sorts of things, such as the fact that the bosons don't get any self-energy. Why not? Because the fermions don't get any divergent self-energy, don't get any divergent self-energy. You can prove all sorts of things that are rather magical and mysterious coming from the symmetry between fermions and bosons. But in particular, you can prove to all orders, no statement, this is true for free field theory, to all orders in everything, perturbation theory, non-perturbative, the whole works, you can prove that if the Lagrangian is supersymmetric, that there are exact cancellations to all orders, which make sure that these divergences don't happen. That's the punchline, and I feel like I've been punched around a little bit too much today. 2 hours of teaching this morning and an hour and a half of supersymmetry is more than I can deal with. I'm sorry. Any questions?
I have an easy question.
Yeah, good.
How do you spell
Chiral, C-H-I-R-A-L.
Oh, yeah.
Yeah, chiral, like your hand, handed this.
Has someone done all this bypassing the Lagrangian and just going directly to the Feynman rules?
Yeah. You can derive Feynman rules from, no, can you, well. No. The way you get Feynman rules is from a Lagrangian. Could I tell you what the Feynman rules are? Sure, but they wouldn't be very interesting. Look, the interesting thing is here is that this is a generalization of space-time. What's interesting here is that this is generalizing our ideas of space-time. It's adding coordinates of space-time. What do you want the Feynman diagrams for? You're going to go and do Feynman diagram calculations. You're going to go up to Slack and say, I'm here, I'm going to do all the Feynman diagram calculations you want? There are people who can do that, and they can do it a lot better than you or me. What's really interesting here is that this is a generalization of space-time. Here it's just time, a generalization of time and new coordinates of space. It's going to be a new generalization of space-time, a new generalization of the symmetries of space-time that will generalize the special theory of relativity to a theory which mixes up the x's with a bunch of thetas. That's what's really interesting about it. It's not just any old set of Feynman diagrams. It's one which comes out of a deep, presumably very, very deep space-time symmetry, generalization of space-time symmetry. So why would I want to give you the Feynman diagrams? What would you do with them?
Sometimes I think that they're more fundamental than the Lagrangian.
I don't think in this case. No, I really don't think so. It's not so much the Lagrangian as these symmetries. These symmetries appear to be really, really fundamental, a fundamental generalization of coordinate shifts, rotations. These are kind of rotations that sort of rotate in a funny way time into anti-commuting coordinates. No, I don't think the Feynman diagrams themselves would tell you very much. They would be very dull. I would tell you this coupling constant has to equal this coupling constant. It would not be interesting. And looking at the Feynman diagrams, you would have no guarantee. Just looking at the Feynman diagrams, you would see no guaranteed reason why all these perfect cancellations take place. You would have to work out diagram by diagram and see that all the divergent contributions to the self-energy of bosons canceled, and it would just be a set of accidents. Just as it would be exactly the same as if I gave you the Feynman rules for, well, if I gave you a set of Feynman rules and you started calculating Feynman diagrams and discovered to your amazement that the scattering amplitudes were always Lorentz invariant, but you had to go step by step by step by step, each Feynman diagram, each order of perturbation theory, you would start to ask, come on, there must be some reason why these things are happening. Why is it that the scattering amplitudes are always the same in any reference frame and so forth? You would eventually come to the conclusion that there were some Lorentz transformations, that the theory was invariant under Lorentz transformations. I could give you the Feynman diagrams of supersymmetry and show you all the cancellations, and you would say, why? I would go back and say, because the theory has this kind of space-time symmetry, this generalization of space-time symmetry. So to me, that's what's interesting. I'm not going to take this much further. I'm going to show you one or two examples of super Lagrangians, and then I'm going to tell you the implications for particle physics, a little bit more about the implications for particle physics, which are not much more than saying that there are all these cancellations which take place, and there are the superpartners. They should be there in the experiment. In the experiments. There's not much more than that. Yeah.
One of the nice things about this mathematics is you don't have to worry about series expansion diverging to infinity. Ever.
Right.
Guarantee you.
That's right. Right.
So you're going to do something similar to the space coordinate as well as
No.
you've done with the time?
No. What do you do with space coordinates? And to expand things. Fourier transform. That's a useful thing to do. It's not particularly useful to power series expand in coordinates. It's just not a useful thing to do. Fourier transform is more interesting, and it gives you waves and so forth. Here, power series expansion in the thetas is the thing to do because it terminates. The power series expansion in terms of x's would not terminate. All right, so it would just be some arbitrary expansion. Yeah.
If a supersymmetric particle shows up in the LHC,
Yeah.
how will we recognize that it's a supersymmetric particle and not just another particle we didn't know about before?
All of its couplings and its interactions with the ordinary particles are determined by the supersymmetry. All right? So all of the terms in the Lagrangian involve a much smaller, in particular the interaction terms, the coupling terms, phi cubed, the phi fourths, the psi phi terms. They're all governed by a smaller number of coupling constants than what you might have. In other words, there are very detailed constraints among the parameters of the particles that have to be respected. So decay rates, cross sections are all determined in terms of a smaller number of constants than the general theory that you would write down of that same set of particles. It'll be clear. It'll be clear that they're superpartners.
So the superpartners actually, as far as we know, don't have the same mass, right?
What's that?
We've been talking about the superpartners having the same mass with the fermion.
That we have to change.
And we don't expect them to have the same mass, right?
Nope.
So how does that complicate the theory?
A lot.
Okay.
We have to talk about the spontaneous breaking of supersymmetry. And we have to talk about spontaneous symmetry breaking of supersymmetry, which itself is a hellishly complicated story. Well, we'll see. We'll talk about it a little bit. No, it's an extremely involved story, and it's extremely frustrating for somebody who likes to teach physics and likes to explain physics. This is incredibly frustrating. It's frustrating because it's just, as I said, it's just a bunch of formalism and index manipulation and symbol manipulation, and in the end, in the end of the day, even after you're finished with it, you have to break the symmetry. That involves a whole theory of its own, and then you have to put it together with gravity. It's enormously complicated, and I find it extremely frustrating, very, very frustrating that something which seems very, very simple, the idea of a symmetry between fermions and bosons, becomes so complicated so quickly that it becomes unexplainable even to people who have learned all about quantum mechanics, learned a bit about quantum field theory, learned about relativity, and still to go through this stuff it really takes a quarter of, not a quarter of this class, but a quarter of a twice a week supersymmetry class to go through this. And even then, it wouldn't be finished. So it's a big subject, and it's a difficult subject, and it's a technical subject, and yet, at some level, it's probably saying something very simple, and we don't know what it is.
Is there any end to the layers of abstraction that keeps piling on and on? Or you just keep going?
So far, no. So far, this has reached a point of abstraction where I think it becomes unexplainable, except to those initiates, people who have initiated themselves by going through. You know how you learn this subject? You learn this subject by going through detail by detail by detail by detail and doing it over and over again until it becomes second nature. And everybody I know who has learned it has complained bitterly about having to go through detail. You don't go through details like that when you're learning general relativity. You don't go through details of index, index and keeping track of signs and keeping track of details. The way this subject was learned by the people who learned it was by going through the details over and over and over again. And it's extremely tedious, extremely tedious. What is it saying? I think it's saying, look, there was no guarantee that the rules of nature wouldn't be tedious, that they wouldn't be tedious having to keep track of detail and detail. It's just what we impose on what we would like when we say that a theory should be simple and comprehensible and composed out of pieces that we can understand. Instead, it's saying it's not very complicated. There's some simple rules, but to follow through on the simple rules, to use them, to construct them, is just an exercise in the frustration of enormous amounts of tedium. The people who did this work really did immerse themselves in a kind of detailed tedium until they got good at it. Once they got good at it, they could look at it and do it much easier than I can. I'm not good at it.
Can we infer something about the structure of fermions and bosons through these transformations that dictates their activities?
What do you mean by their structure?
Well, the fermions and then the bosons, they interact quite differently with each other, right?
Yeah.
But we're seeing in this theory that they are, swapping. You have the fermion and boson pair that are somewhat the same thing in some regard, just two different sides of the same thing, right? So does that tell us?
Well, they're images of each other under these transformations.
Right. So does that tell us something about what the differences are, the characteristics of the fermion and the boson?
Does it help for me to say that a fermion is what you get when you take a boson and act with the generator Q? No. Well, does it? I don't know. In some sense, to go from a fermion to boson is the process of shifting theta a little bit. The shift in theta from one, you can't really speak about the values of theta. They don't take on values in the usual sense. But this shift operation, which shifts theta a little bit and at the same time does this over here, that is the operation which takes you from a fermion to a boson. So it's a little motion in this superspace. A little motion, roughly speaking, from one point of superspace to another point of superspace takes you from fermion to boson. It is analogous to the way rotation of coordinates will take the x component of a vector to a y component of a vector. Right? The x and y components of vectors you can visualize in your head. The fermions and bosons are often called components of a superfield. That superfield up there, the phi, the psi bar, and the d are the components of the superfield. They're called the components of the superfield. And the supersymmetry transformation sort of mixes one into the other, takes one into the other. In particular, it always takes a phi to a psi and a psi to a combination of phi and d. So it just is a motion in the superspace which takes a fermion to a boson. Can you picture it? Can I say what that means about these particles in any language that you can understand? No. The language is not English. The language is Grassmann variables and this is why you don't, I was going to say this is why we don't teach it in courses like this, but there are no other courses like this, so I think But this is why I have hesitated and sort of worked around it and avoided it. But you asked for it. All right, so I'm not going to stop until it's finished. And string theory is not as bad as this, incidentally. String theory is much easier to understand.
For more, please visit us at stanford.edu.